All right, welcome everyone. So we're going to look at an example here where we will use what we know about energy and about simple harmonic motion to solve this problem. All right. So here we have a 1.5 kilogram mass, and it slides along a horizontal frictionless surface at a speed of 2 meters per second until it collides with and sticks to the free end of the spring. And we're told the spring has a spring constant of 50 newtons per meter. The spring's other end is anchored to a wall. How far has the spring compressed with, when the mass is at least for an instant at rest? And how much time does it take for the spring to compress to this point? All right, so looking at this, I think we're going to draw a couple diagrams. All right, help us visualize what's going on. So the problem does tell us that, let me actually switch to a thicker pen here, that we have a mass and it's traveling along and it's headed towards a spring, where the spring right here is relaxed. It's attached to a wall, so we'll kind of draw some lines here to represent that the wall doesn't move. All right, so that's great. So this it's headed this way. When it's headed this way, we know the speed is 2 meters per second, so maybe we'll jot that down. And we also, let me write here, V for speed. All right, we also know that the spring has a spring constant of 50 newtons per meter. All right. Now let's see. So looking at the problem, at least the first part here, how far has the spring compressed when it's at least for a moment at rest? Well, visualizing what's happening here, right, our block's coming in, it collides and sticks with the spring starts to compress, slowing the block down until the spring is fully compressed, and that's when the block will be momentarily at rest before then it gets sprung back the opposite way. So the other moment in time we're going to be concerned with, sketching this out, is when our spring gets fully compressed and the speed of our block is 0. So that'll help us figure out then how much it compresses by. All right, let's see, anything else I want to jot down here? Ooh, looks like we also know the mass, right? So maybe I'll write that off to the side. Mass is 1.5 kilograms. All right, so we're going to use energy to solve this first part of the problem. All right, so something just to note, all right, whenever we're dealing with energy, we want to define our system. So let's define our system to be both the block and the spring. All right, because this way we've got no external forces doing any work, and energy is conserved. Sorry about that. All right, so energy is conserved here. So we've just picked 2 moments in time that'll be useful for us when problem solving. All right, so for sure, we're going to want to take the moment in time when the spring is fully compressed. All right, so we're going to take the energy at maximum compression and set that equal to the energy at some other moment in time. Well, looking at what the information we know, well, we don't really know much else except for that the block was moving at 2 meters per second when it hit the spring. Well, that's interesting, because when the block hits the spring, we know that's where the spring's in its relaxed state. It's at the equilibrium position. That's when speed's its maximum value and there's no potential energy. So let's set that equal to the energy at equilibrium. All right, this will be useful for us, right? So at maximum compression, we have no kinetic energy, but we have spring potential energy. That's equal to 1/2 the spring constant times x squared, where x is that value we're looking for, the maximum compression. You can even call this the amplitude if you'd like, because that's what it is for simple harmonic motion. And that's the energy at equilibrium, At equilibrium, there's only kinetic energy, so that's equal to 1/2 mv squared. For v here, you could write this as v max, because that's also true. That's that 2 meters per second. Alright, so looking here, we can do a little bit of math and rearrange. The halves cancel. We're solving again for how far the spring compresses. That's x. X will give us, skipping over the algebra, mv squared divided by k. So all we need to do here, because we know everything here, right? We just need to plug it in. So our mass is 1.5 kilograms. The speed at equilibrium is 2 meters per second. Square that. Divide by the spring constant, which is 50 newtons per meter. And we plug that all into our calculator, and we get 0.35 meters. So that is how far the spring compresses. All right, awesome. So now we're on to the next part of the problem. How much time does it take for the spring to compress to this point? All right. Well, let's see. Usually when we think about time, our mind immediately goes to kinematics, using kinematic equations. But we're dealing with a spring here. There's a problem. Right? Remember, we can only use kinematic equations when acceleration is constant. A spring, the spring force changes with respect to position. So that means the acceleration changes as the object compresses. Right? We know that. We see that with the simple harmonic motion equations. The acceleration function is sinusoidal. So we cannot use kinematics. So we'll just use our knowledge of simple harmonic motion to solve this. Right? Because the time it takes to compress is some amount of the total period. All right, so thinking about this motion, all right, so let's say our object just collided and stuck to this relaxed spring. So let's say we kind of start there. It compresses all the way, gets stretched back to equilibrium, then moves beyond that to its maximal leftward location when the spring is stretched out, then goes back to equilibrium and then repeats. So in terms of how much this compression is of that total period, it's 1/4. So the time to compress is 1/4 of the period. So this time is 1/4 of the period, so that's 1/4. Well, we know the expression for the period of a mass on a spring. All right, that is 2 pi times the square root of m over k. All right, so our time then here will be 1/4 of 2 pi is pi over 2. And we plug in m and k. So we have 1.5 kilograms, our spring constant of 50 newtons per meter. Plugging that all in our calculator, we get 0.27 seconds for the time it takes to compress. All right, so I hope that was helpful in problem solving. Now we could make this a little bit more complicated if you wanted to. Oh boy. Right. In the sense that maybe we could ask another question, and a very common question that's asked is, where in this object's motion is the kinetic energy equal to the potential energy, or something along those lines? Right, so sometimes in a problem like that, we may not be able to choose a moment in energy conservation where we simply just have one energy term. We might have to consider a location in which there is both spring potential energy and kinetic energy. Right, so maybe our spring here is partially compressed, so there's still velocity and there's also spring potential energy. Right, so there the math gets a little bit more annoying. It's not as ideal, but it's still doable. All right, thanks for listening.